samples in the auto sample time counts. Whatever, I mean, they just fit in the rad. We'll calibrate off a standard. So the system's automated. We'll just go to each sample and do the analysis fully automated. You don't have to sit here and change like pump or whatever. But you have a pump here. The sample gets sucked up by the pump, and you'll notice it's just liquid flowing through the tubing. Once it gets to this point, we want the sample's nebulized. So if you look really closely in this glass thing, what you'll see is like a tornado of mist taking place in there. And if you really look closely, you can actually you'll see. It helps if you get a light shine on it, but essentially what you have here is as the sample comes in, it goes over a high velocity gas and it nebulizes the gas, meaning that your sample is just made into really basically a mist of sample or a fog of sample, and a little bit of that is carried up into the instrument and carried into a plasma. If you look in this window, you can actually look in there and you can see what looks like kind of like a candle.
Question: Who wants to do the blanket standards data?
What?
Because somebody to analyze the blanket standards data. I mean,
Blanket standards? What?
As far as, you mean calibrating or?
no, I mean somebody to take those data and analyze and average it and stuff like that.
Right. Yeah, somebody needs to do the data. Anyways, well, let's get back to that. That plasma there is an argon plasma, meaning we pump argon gas into an RF, or radio frequency area. And what it does is it vibrates the argon molecules to the point where it basically heats them up and they lose most of their electrons. The interior of that plasma there that you're looking at is somewhere between 5 and 8,000 degrees Kelvin. Okay, that's pretty hot. That's the type of stuff like you can weld with. Right, but it's contained nicely. The whole design is to keep the quartz tubes from around it from melting and stuff. So what we're doing is these elements flow into that plasma. There's enough heat there to break them into individual atoms. So instead of like in a solution where you have water molecules bonded to the metal, you have organic molecules that might be bonded to the metal. Once you get into like 6,000–7,000 degrees Kelvin, all the atoms, it's hot enough where they get busted into individual atoms. There's nothing coordinated to them, and at that point, thermal energy goes into them. The electron configurations get excited, they drop back down to ground state, and they emit a specific wavelength of light. The amount of light they're emitting is directly proportional to the amount of metal that's being pumped in. So basically, by monitoring the emission of light at a specific wavelength, we can determine what the concentration of the metal is in your sample. So it's pretty straightforward. And then from there, we just have a fully data automated system that processes the data, spits out the results, and it's all up to you then.